welcome to the first post-Kansas Fest 2022 episode of Buried Treasures. So I'm going to go over some programs that I've written that play Midi music on an Apple IIe or a 2GS, but we're going to start with a song from Elvis that expresses his sentiment on the end of Kansas Fest 2022. So what we are looking at now is the bat file that starts up the MIDI system. And the first line, if you calculate that out, you get BEF8, which is a PRODOS pointer to the free buffer routine. So it will free any existing buffers, and then it's going to run the copy command, and then it's going to start loading our files. So it runs router.object, and then it runs allocate and allocates 6 pages. Then it runs auxload, then it allocates 10 pages, then it runs object load and gives it a starting address of 33,792, and then loads these objects, which are the machine code for the system. 1, 2, 3, 4, 5, 6, 7. So there's an interrupt driver, MIDI filtering, managing notes, control changes, program changes, sysx changes, and managing the interface, which is the Passport MIDI interface, which is configured in advance to the slot of the MIDI interface. And then it copies the files needed for the system to the RAM disk. So it uses RAM AAPC, which came from the PC transporter, and you can rename RAM 5 or any other RAM disk to that name to use this system. So like there's a MIDI information reader to kill a song and go back to a menu. dir.object gives you a menu of songs. There's a library program for you know, looking at directories and picking a song, and then managing tracks, playing tracks, a control panel, multiplay. So all these things were developed over years in the 1990s. And then it goes to a initial prefix and then runs the library program, which gets the system started. Okay, so let's exit to ProDOS. Control Q, J, yes. And let's start up. Let's go to a basic system. Okay, let's reboot slot 7 drive 1. Let's just boot ProDOS. Okay, and then go to basic system. So I'm just going to answer the prompts to start up that system. So M is the MIDI play system, and it just ran that executable file, and it just loaded the objects. Now it's copying the files to the RAM disk, and here we are. Now under the hard directory, so it only shows locked directories. So in the MIDI, here are some popular songs. Let's start up something from the 70s. And let's run Telephone Line, a song by ELO, the Electric Light Orchestra. Okay, so this is the MIDI info program that is looking at the MIDI file, and then if you had a whole bunch of tracks, you can choose which ones to manually assign, up to 8 tracks for the player. And then we're just going to say automatic, and it's a type 0 file, so it's only 1 track. So you hit enter, and then it's going to load the track into memory and start playing the song. So these programs were written by myself for myself because I had an Apple IIe with a Passport Midi interface and a PC transporter, and I wanted to play Midi files. So when I looked at it years later and realized, okay, it's not totally configurable, I wrote these instructions about how to configure the program for a new slot, and it really is patching certain locations in each object. So another goal of writing this system was to learn object-oriented programming and figure out how I could do it in Apple machine language. So there are objects in the system that communicate to each other via small little messages. So let's look at the catalog. So this is the catalog of the MIDI play. And let's look at the allocate basic program. Okay, so here it's using a machine language routine to allocate pages of memory, and then it tells you what base address you got. So let's do this. Let's run it, and let's say allocate 5 pages, and then let's look at the 300L to look at the code. So it's jumping to BEF5 to get memory from ProDOS, and it's passing in the A register the number of pages, and if the carry is clear, that means it worked. And 308. Okay, so let's see, at 308, it stores that at 30F, it stores the accumulator and prints it. That's the starting address of the code. So here it got a 95 as your starting address. So it's really moving the buffers down, or whatever ProDOS does, to allocate memory safely for your code. So that's nice. So here is another basic program that loads objects into memory. And you saw this running. It's reading the directory and then displaying it on the screen. And then it is prompting you to select an object in the line 100. And it is taking the starting address that the executable file passed in at line 96. Then it checks the file name, whether it found it or not, if it's a binary file or not, and then it's running that file, that object file, at the address that it has calculated. So it's determining the length of each object from the catalog at line 180. Because when it did the catalog, it was able to read it into variables. Let's take another look at that. So it's inputting L sub I at line 55, the value of midstring L string 65, 7. So when you type catalog, the length end file is in the next to last column. So it's actually using that length from the catalog to figure out where the length of the object. So you could see, like, if you look at the first few lines, there's several .obj files at 6,000 hex, and the lengths are small, except for track manager.obj, because that's managing all the tracks and how they get played, or how you read data off of tracks in the MIDI file. And it's fascinating. The dir.object is also big because that is what draws that directory in 80 columns where you pick the file that you want. So this allowed me to write small source files. So like Note Manager is only 494 bytes because it only has a few specific tasks to do. So it's So these are more like static classes than objects because I don't instantiate the objects, but I was able to, based on my understanding of object-oriented programming, code them so they could pass messages. And then I figured out how to connect the objects together to execute what I wanted to do. Back in November 27th, 1992, Thanksgiving weekend, I documented the system. So, object-oriented machine language, wow. So these are my ideas of how this thing would work. A bootstrap process would set up the OO environment by allocating memory from the operating system and relocating the OO driver code. Okay, that makes sense. So that first you need your object-oriented driver in memory with a pointer to it that everyone can call. So programs are set up as entries in the object table. So I'm sure this type of idea goes back to the 1940s even, about a table of subroutines that you call. Okay, so as objects are loaded into memory, their names and addresses will be maintained in an object table. And due to limited memory, each entry in the object table will have 6-byte object name and a 2-byte address pointer to its code. Yeah, memory was expensive back in the days. So I gave myself up to 256 objects that I could create. And then if the first byte of the entry is 0, the entry is free for use. That's interesting. So I could deallocate objects, but then you have memory holes to manage. So I didn't do any garbage collection there because I just needed what I wanted. So the entry is 6-character name in high bit ASCII. That's the Apple standard. And the address is stored low byte, high byte. Object code can only be invoked by sending messages. The message format and interpretation is completely determined by the receiving object. However, a protocol may be established to use the first byte of the message as a phase number to determine which part of the code gets executed. Yeah, because like you may call a message at one point and then later you want it to do something different. So you define those bytes, and I made it freeform. Because I only needed this for myself, not anybody else. So to send a message to an object, you jump to a subroutine in the object router, and then the 6-byte object name, and then the format of the message is all the bytes after that. So it figures out what to do based on the data passed to the object. So what the message subroutine does, it will copy the message into the receiving object's message data area, adjust the stack pointer to return to the code following the message, and JSR to the receiving object's code. Interesting. When the receiving object completes, it could do an RTS to return to the caller. It may pass a response back to the caller via the registers or status flags. The red message handler preserves them. Okay, good. So the message handler address will be set up as a jump vector in 0 page. And in BASIC, I think I changed it from the ampersand to the user vector later. So a string is passed containing the object name and the message data. So that invokes the code to read the string and invoke the object. So I think the reason I changed it to the user is because you could pass a number in the user parameter, and that would correspond to the object number. So these objects were assigned numbers as they were built. So here's your sample header code and mainline code. So this is a template that I used for building new objects. So you jump to the message subroutine, and here's the ASCII O setup is the object's name, and then some sample parameters. So like say you wanted it to read that string and do something with it, and then you return, and let's see, jump vector to the mainline code of the object, which is, okay, I'll bring it to the top. So that jump is to where the cursor is, a few lines above it. So when it's invoked, it jumps to that code. And then there's a message length and a message data area. So this must be observed, where like if you have 5 bytes as a message length, and you have to have 5 bytes afterwards. And you could have optional internal data maintained by the object as additional bytes. So those would be local variables only accessible to the object, or private. So here is sample code for implementing phase processing. So here you're seeing that it loads the phase number from the first byte of message data, compares it to phase 0. If it's not equal, it goes to code 1 sample, but if it is equal to 0, it jumps to the P0 sample code at the bottom. And then it compares, if it's not a 0, it compares it to 1. If it's not equal, it goes to C2 sample. Otherwise, it jumps to P1 sample. And then at C2 sample, it's an invalid phase, so it breaks. And then the programmer would have to debug that, why an invalid phase number was passed. So now you see the structure of object-oriented machine language, and I could go into more detail in future videos if there's interest. I've been sitting in this box since my owner packed me away. It has been so many years, now I have a lot to say. Will someone rescue me before I go to the dumpster?
or the e-waste recycling plant, where they'll pull my components apart. So here I am, and can you please tell me, whoa, where do broken computers go? Can they find the chips they need? Or will they be waiting for months until they arrive? And if somebody loves them, will they find a forever home? I see them on Twitter, and my heart just weeps for them all day. My capacitors are dry, and my legs are all corroded from the battery that leaked after my owner boxed me up in the humid heat of the basement. The battery exploded, spreading all its sticky goo. Now we need to wash the gunk off, but I still work, and won't somebody repair me? Whoa, where do broken computers go? Can they find the chips they need? Or will they be waiting for months until they arrive? And if somebody loves them, will they find a forever home? I see them on eBay, overpriced as they just sit unplugged. Watch Retro Repair Roundup Sunday nights twice a month. Watch it and support them, they keep us alive, alive. Whoa, these guys are amazing, and the guests are doing great work, rescuing old computers and bringing them back to life. They got all the modern tools, and the bench cams magnify us. It's like watching surgery while you fold your laundry. Hooray, hooray, thank you so much. You still care for me.